Hello everyone. Now in this lecture 3 we are going to design for Zero ISI with the help of a Nyquist criteria here. So we had seen some of the factors regarding the ISI and how this ISI can be eradicated that we can design now with the Nyquist criteria here. The first one, the bandwidth of the channel, which is the Fourier transform of the signal at the output of the receiving filter, is given as, okay, the receiving filter what we had discussed. So that time x of f is equals to gt of f, c of f, g r of f. So this one is from the transmitter, this one is from the channel, this one is from the receiving filter. So the output what we are getting, and this will constitute from due to the help of the Fourier transform, we can say this is the thing. Now we can replace the c of f by c naught into e raised to the power of minus j2 pi f t naught, where we have concluded for to eradicate the ISI, to make a zero ISI, we have to make c naught is equals to 1 and t naught is equals to 0, where gt of f and gr of f denote the frequency responses of the transmitting and receiving filters, and c of f denotes the frequency response of the channel. So this we have deal with in the previous videos there, right? Or this all the terms we had derived there. Now for convenience we set c naught is equals to 1 and t naught is equals to 0. For convenience we set c naught is equals to 1 and t naught is equals to 0 when output of the receiving filter is sampled periodically, that we have derived there. So what is happening here, the concept of the lecture 1 is utilized in the lecture 2 and the lecture 2 is utilized in the lecture 3. So they are all interrelated here. Periodically at t is equals to mt yields to an expression ym is equals to x naught am plus the summation of n not equal to m of an x m minus n plus wm. So this way again we have seen this equation where the first term of the RHS is the desired symbol, the second term constitutes the ISI, and third term is the additive noise. To remove the effect of ISI, it is necessary and sufficient that x m capital T minus nt is equals to 0 for n not equal to m and x naught not equal to 0, where we can assume x naught is equals to 1. So we can assume this one as x naught is equals to 1. So we now need to remove this term, the 0 ISI, make it a 0 ISI. We can make this one as 0. We should make them, especially we have to make them as 0, and then we can assume that y x naught is equals to 1. So that time the overall communication system has to design such that x n of t is equals to 1 for n is equals to 0, 0 for n not equal to 0. This is what the condition we have derived, and that we'll be using it for the Nyquist criteria. So this is what the sufficient condition for x of t, and I'll be going for the Nyquist criteria there. Then the necessary answer for how we can find, that is x n of t is nothing but 1 for n is equals to 0 and for 0 for n is equals to not equal to 0. For other than n is equals to 0, it should be 0. So that time that condition will make that the 0 ISI is not there. That is, only the first term has to be 1, x naught is equals to 1, that time only it should be there, and if n is equals to 0, it is 1. That is what the desired signal. If it is other than that signal, that is like n is equals to 1, 2, 3, so that time if you have any kind of a value there, then it is saying there is a presence of ISI. So this is implementing that no 0 ISI is present, and that its Fourier transform x of f must satisfy summation of m is equals to minus infinity to plus infinity x capital X of f plus m by t is equals to t. Okay, now suppose that the channel has a bandwidth of w. Now suppose that the channel has a bandwidth of w, then C of f is equals to 0, then C of f is equals to 0 for mod of f greater than w, that is the frequency, if anything greater than the bandwidth we are saying. Consequently, x of f is equals to 0 for f mod of greater than w. Under this condition, we have three cases. So we had to be strict to some rules that C of f is equals to 0 for f greater, anything outside the bandwidth is 0, and x of f anything outside the bandwidth, again it should be 0. Then we have three cases. Now this first case is the t less than 1 by 2 w or 1 by t greater than 2 w. So what is this happening here? This is the condition what we have done, and this is the bandwidth. So here at this rate there exists no pulse whose spectrum replicas add to form a flat spectrum, and ISI is inevitable. ISI is inevitable at this rate. You can see it here. Instead of this waveform, this is a flat spectrum. Actually the waveform would be like this way. Okay, actually the waveform would be like this way, but due to this the flat spectrum technique of this one, so all the waveform has become the flat here. And this rate, what is happening, there will be a bandwidth, so there will be no interference as there is a space between those things. So ISI will not be generated, where the condition is like this, that t less than 1 by 2 w or 1 by t greater than 2 w. Next one, if t is equals to 1 by 2 w or 2 w is equals to 1 by t. This is intervals, okay? This is just we change it and we get like that, we can interfere. So this is the spectrum. So we can see here again the spectrum is like this way. Okay, again it has been made flat. So sometimes what is happening, this while generating this signal, if the waveform is exactly here, we know we cannot design the exact thing. Sometimes there might be like this way the waveform, sometimes this waveform might be generated like this way. So there might be a ISI here. This will be the ISI. There might be a chance, but as per our practical consideration, I'm not telling, I'm telling in terms of a theoretical thing. So here what we can say that at this rate there exists only one x of f, and that results in z of f is equals to t, namely x of f is equals to t which is less than omega, that is the w here. Now and this 0 otherwise here, so now which results in x of t is equals to sinc t by t, or x of f is equals to t pi of f divided by 2w. So what you can infer from this above result, that difficulties with the sync pulses. Okay, difficulties with the sync pulses. So this is what the sync pulse, and how the sync pulses will cause an ISI here. So that's the problem here. So now it is non-causal and therefore non-realizable. A possible solution is delaying its until to so that it is approximately 0 for t less than 0. But of course mt stands for mt plus t naught, because here we can relate it saying that mt also is equals to mt, but make it that t naught is 0 here, and it decays as 1 by t. A small mistiming error in the sampling of the output of the Mach at a demodulator results in an infinite series of ISI components. The series does not coverage here. So that what is trying to say, that when you have a sync of pulses, it will definitely spread on to the other signals. So that time when it causes the interference in the other symbols. So this is what the problem here. So sometimes this results in the sync pulses. The sync pulses is what? as I told earlier, the small error might interfere with the other signal. That is what we are trying to do. Because of this, the mistiming of error. The t greater than 1 by 2w or 2w greater than 1 by t. So this is the another third condition, which is also one of the important, and this we'll be using it in an equalizer system. Now you can see, I know looking at this waveform, it will definitely, again it is causing a interference here. That is we call it as the ISI here. Okay, that is again we call it as a ISI. Okay, so what is happening here? Then you can see here. You can see that is what again this is because this part, every signal of this part is causing us some kind of interference here. You can see it here. You can see it here. Okay, so this is again the ISI. So this how we can be eradicated. So this is one condition when the t greater than 1 by 2w or 2w greater than 1 by t. So that time at this rate there exists an infinite number of choices for x of f such that z of f is equals to t. There exist numerous pulses which satisfy the zero ISI criterion. A popular choice for x of t at 1 by t less than or equal to less than 2 by w is the race cosine spectrum. I think this kind of things will be illustrating in your labs. The race cosine spectrum will be there in your advanced communication lab, where how this waveform can be like different factors, the role of factors, again the factors will come. So it will resembles the race cosine spectrum. So xrc of f is equals to t for 0 less than or equal to f mod of f less than or equal to 1 minus alpha divided by 2t. T by 2 is 1 by plus cos pi t divided by alpha mod f minus 1 minus alpha divided by 2t 1 minus alpha divided by 2t less than or equal to mod f less than or equal to 1 by 1 plus alpha divided by 2t, or it is 0 for f mod f greater than 1 plus alpha divided by 2t. So here that alpha is called as the roll-off factor. Alpha is considered as the roll-off factor, which takes the value in the range of 0 to 1. So alpha is like equal might be in the range of 0 to 1. So the pulse x of t having the race cosine spectrum is x of t is equals to sine pi of phi t of d t divided by pi t of divided by t into the cos pi alpha t divided by t divided by 1 minus 4 alpha square t square divided by t square. That is equal to sin t by t into cos pi alpha t divided by t divided by 1 minus 4 alpha square t square divided by t square. So I can represent this the whole terms in this terms of a sinc function. Okay, so this is we call as a again the race cosine spectrum also we can receive. So we can the sinc function can be observed it here. Here you can see here. Okay, the first how the waveform the sinc pulses it will be there. So this is what alpha is equals to 0.5, then alpha is equals to 1. We cannot categorize here in the time domain. So what we can do is like alpha is equals to 0.5, you can observe it here, and alpha is equals to 0. So we'll have a standardized. So we'll come to this in the frequency of the spectrum part. that you can see it here. Okay, so it has been differentiated. So there, so alpha is equals to 0 standardized, and alpha is equals to 0.5. Alpha is equals to 0.5, and alpha is equals to 1. You can see here, if you increase the alpha is equals to 0, it was 0.5, it will be here, alpha is equals to 1. So if you increase the alpha, if you see, so it will be more there. So that time the alpha is like 0 here, so we can see 0.51, 0.75 might be here, 0.5 might be here. So we can see that how the roll-off factor is making the effect in this spectrum. Okay, then so you can see it, alpha is equals to the 1. Now is there, this is 1, the alpha is equals to 1. So like here, different factors, it will be affecting those things. So now we have to consider the benefit of the, what are the benefits of the race cosine function spectrum there. Okay, now first, the benefit of a race cosine spectrum, it decays as 1 by t cube for alpha greater than 0. So any sampling offset results in finite ISI. Okay, so any sampling offset results in finite ISI. So if it decays as 1 by t cube, so it's in the powers of a t cube. For alpha anything greater than 0, for any offset, the rate is 1 by t cube. And it results in the finite ISI. With larger I alpha, the pulse decays faster, but the bandwidth utilization is poor. That is what I am trying to say. If you increase the alpha again, the pulse decays faster, but the bandwidth utilization is very big and poor. So that is another point here. Okay, it is possible to design practical filter that implement the raised cosine pulse. It is possible to design practical filters that implement the raised cosine pulse. What is this point we say? So how x of t is equals to transmit pulse, the channel receiver filter, so that is equal to gt of t into the ct of t into gr of t. And this how we have the practical filter has been designed. It's a raised cosine pulse, so that the waveform will be there. So the overall impulse response of the system is then raised cosine. Okay, this is another observation. What we can see is a raised cosine here. For ideal channel C of f is equals to 1, we have XRC of f is equals to GT of f into GR of f. GT of f, GR of f. If the receiver filter is matched to the transmitter filter, then XRC of f is equals to GT of f into GR of f is equals to GT of f the whole square, the mod of this. So that time what is that? So the value, all it will become the same. So ideally GT of f is equals to the square root of the mod of XRC of f, then it is multiplied with e raised to power of minus j 2 pi f t naught. So you know this how to nullify this way. Why? When a delay is 0, so we can make it a response, the receiver filter is equal to GT of f. Now this the transmit pulse is a root raised cosine pulse, root raised, so that you can rectify those things. So now here we have been categorized in the 3 different Nyquist criteria, and how the difficulties and the benefits of the sinc and the raised cosine pulses respectively we can be understood, and how it can be utilized to solve some of the make a zero ISI. So to have a ideal channels, to have a calculation, so how to with the bandwidth utilization, how the offsets of the finite ISI will make it effect of this. Okay, so this is all about the concept about to the zero ISI, the band limiting signal for zero ISI, and for making with the help of the Nyquist criteria here. Thank you.